Okay, I'll start. So we're very happy to have Pratik. We'll be giving us two talks today. This is the first talk. The second one is at 5 o'clock, also here, right?
Yes.
Okay, great. So Tensor networks and numbers.
Thank you so much. So this colloquium is meant to be a sort of broad picture view of the sort of work I've been interested in and that I've been doing over the last few years. And in particular, it's what I call the quantum information road to quantum gravity, which is applying quantum information theoretic tools to understand quantum gravity. So first, let's start with understanding why quantum gravity. Well, at this point, our description of nature at the fundamental scales is such that we have two very successful, I may say quite successful, but incompatible theories. So in particular, we have quantum field theory, which has given us a framework to describe local quantum physics at short scales, and we've had a lot of success with. See the point? Yes. With it. So in particular, two successes are the standard model of particle physics. Here we see the discovery of the Higgs, and also describing in the condensed matter perspective exotic materials and their phases. So in particular, superconductors. So that's great. We also have general relativity, which describes classical physics of large-scale structure of a universe. Two successes of that of late have been our understanding of black holes, which have been seen by the Event Horizon Telescope, and an experimental observation of gravitational waves. So really successful theories, but they're incompatible. So what's the problem? Well, the problem is putting them together has been a challenge. The combination of GR and QFT is fine as an effective field theory. It can be useful for certain things. For instance, in inflationary theories, people have used it to try to understand how quantum fluctuations can give rise to the large-scale structure of our universe. But that's not the complete story, because we know that this is not what's called a UV complete theory. When you try to put GR and QFT together, you run into divergences and they don't seem compatible. And as I'll try to explain, it's probably a deeper problem than just that.
Could it have been that gravity was a classical theory and the rest of the world was fine?
Well, there's lots of problems with trying to do that. It depends on how you try. So I should say that there are still people trying to do that. There are still people trying to have this semi-quantum theory where you have classical gravity and quantum everything else. You often run into issues with irreversibility or violating the uncertainty principle. It depends on how exactly you couple those two things, but unitarity is a problem in this. You can't. So unitarity. So because you have a quantum theory which is evolving with unitary dynamics, classical. When you couple them together, you can lose information to the quantum. It depends on how you do this.
But you could imagine that the Hamiltonian for the rest of the system was just a nice unitary Hamiltonian.
Yeah.
Just that the gravitational field was like a parameter there. Then evolution would be unitary, right? At least nine.
I guess it comes down to the question of what it means. Are we allowing the gravitational field to effectively measure things which are quantum mechanical? So for example, if I have a bell pair which is separated by a large distance, can the gravitational field make a measurement?
If you have to, it's nothing.
No, it's fine. It's fine. I think it depends on how exactly we do it, but either you'll run into issues with if the typically people say that there's this result that if the gravitational field has the capability to entangle things, then you can have things like non-locality and superluminant signaling. But I think it depends a lot on the details of how exactly we do it.
Excellent.
I guess there is something. This is okay. I am not in the field, so that's this question will be relevant. So can you use the gravitational as a perturbation of your field theory?
Yeah. So that's sort of what this means. So when we use it as an effective field theory, we say that we treat gravity perturbatively, treat it as just some other quantum field. This is fine as an effective field theory. The problem is when you try to UV complete it, it's a non-renormalizable theory. So in the sense that it doesn't arise from some well-defined theory from which we're deriving this effective theory. We can treat it as an effective theory whose completion we don't really know. And there's good reasons to expect that the completion is not just a quantum field theory of gravity. It's probably something different from quantum field theory.
In general, let's say it's that simple quantum mechanics what we learn.
Yeah.
All of the quantum mechanics, all this work is based on the quantum theory.
Yeah, that's right.
So why not these also can treat about that way?
Yeah, we can. It depends on what sort of question we want to answer. So I think, like, for example, if we just in the solar system want to measure like the quantum effect of something, some perturbation or something, I think that's fine. But perturbation theory breaks down when these things are strongly coupled. So for example, if we go back to the early universe, which is what I was just going to say, it's not any more treatable by perturbation theory. So you're fine all the way up till that when the perturbation theory is okay, but then let's say you go to shorter and shorter scale, at some point it breaks down and you need something more complete to describe that. So as I was saying, we still would like to understand other questions such as the origin of the universe and what happened at these really short scales around the time of the Big Bang, or why we see the particular parameters we see in the world. We have the standard model, but we'd like to explain why we see the electron mass being so and so, or cosmological constant, which is causing the acceleration of the universe being so and so. And so in order to do all of that, we need some sort of more complete theory, which puts quantum and gravity together.
So,
But just, sorry.
can I? Yeah. In other words, you are imagining that this entire quantum gravity or relativity should naturally explain, why the dark energy, what the value was, and all that.
That's the hope.
Because any measurements can be usually explained using effective field theory.
Yes.
That's what whatever we can measure, we'll try to come up with.
Right.
Even the gravitational waveform you actually show actually can be done with an effective.
Yes.
If you don't have enough.
Yes, absolutely. So, I mean, we can think of the standard model as an effective theory as well. Like the standard model is probably not the complete theory of the universe, but there's some parameters there which we've measured and put in there. But you'd like to understand at a deeper level why these parameters, why not something else or something like that.
But that's then an additional condition of putting, right? I mean, I can understand putting gravity and quantum field theory together are required. But this is just you want all the. I mean,
well. Okay, that's true. So you could imagine you come up with some quantum gravity theory which still has some random parameters in there, and you have to say like.
Then, as you said, standard model is a perfectly valid.
Absolutely.
And then it becomes a.
I think if we were in a world like that, then I mean, I think we would still ask those questions. I don't know if we would make progress on it.
I'm just saying that there's a different problem from.
I agree. These are different questions. Yeah, I mean the hope. Well, okay, good. So it's like string theory, for example, is an attempt at this, and in that situation, like it does both at the same time, sort of like because it's putting quantum and gravity together, and it's trying to. It doesn't have free parameters. It's like trying to explain that. You could imagine situations where you solve one problem and not the other. That could happen. I'd like to answer both questions, so that's why I'm interested in this. But it could happen that you solve one and not the other.
Okay, let's say your standard model has all these parameters and you would like to explain. Now, where is this coming that putting gravity and quantum field theory together will help you answer that?
Yeah, good. So I think it's related to, okay. I wanted to say, so in string theory, there's this idea of the landscape, so which is that string theory has multiple solutions, each of which has these different parameters. And string theory, I guess maybe I should say we want a fundamental theory of the universe. Maybe quantum, I mean, it just so happens at this point that we haven't been able to put quantum and gravity together, but as we were saying, like you could imagine we put them together, but you still have things to explain. And so that's a deeper question in some sense. And like,
So just to put again, just back, this theory you're talking about will not explain why the G has a certain value in our universe. That can be done in a different way.
That's right.
Because for evolution of the stars and everything, those things will have to be very specific, otherwise we won't exist really.
Yeah.
But that's not what you're trying to understand by quantum gravity?
Yeah, that's right. So I'd like the more easier question, I guess, of trying to figure out how to even put quantum and gravity together.
Yeah, so the why is a problem.
The why.
Why we see the parameters.
Yeah.
You don't want to go there.
Not yet, at least. Yeah. Maybe I first try the first problem and then figure out the rest of it. Yeah.
I think that's.
Okay. Okay, good. Now, of course, this is a hard problem, and sorry. So I was saying that black holes have. Oh, sure. They've served as a useful playground, and in particular, there's this aspect of black holes, which is black hole thermodynamics, which has helped us try to understand features of putative quantum gravity theory. Again, okay, I'll just, it's fine. So black hole thermodynamics is the remarkable insight that just came from a bottom-up perspective, in the sense that we just try to put together quantum field theory with gravity and come up with this insight without actually having a full quantum gravity theory. So it's a statement that's sort of agnostic to what quantum gravity theory you believe in. And it's the insight that an entropy can be associated to a black hole, so that the total entropy in the universe is the area of the black hole over 4G plus all the entropy that's outside, this is called the generalized entropy. This was the insight of Bekenstein and Hawking and a lot of people in the 70s.
So in the sense that if you define these quantities,
Yeah.
those are equations similar to entropy
Exactly.
in thermodynamics.
It's like an analogy at this point. Yeah.
Can I ask you something about that? The coefficient 1/4 G.
Yeah.
That actually requires you to consider quantum effect.
Yes, that's right.
And so it's not just classical.
No, I mean classical coupled to quantum matter. Yes.
And sorry,
Yeah.
just to go back to Firaz's question,
Yeah.
if gravity was not quantized,
Yeah.
would black holes evaporate and give out gravitons?
Well, they don't
Or
need
would
to
they
give
give
out.
out any gravitational radiation? As per Hawking, what would Hawking's calculations say?
Well, they would give out whatever quantum matter you have, like they would evaporate.
Would they give out any gravitational radiation? Sorry, just to not to put you on the spot, but just to ask you. Suppose
If we really treat gravity classically, there's no, like you really need some sort of tunneling process in order for things to escape. So classically, whatever a gravitational wave inside would be cannot escape. So in that sense, no, but I think it depends on, how this dynamics works. But I would say no. All the quantum stuff can escape by tunneling out, but anything classical shouldn't be able to do that with classical.
Thank you. Sorry, won't come back. This.
So how general this is called the Bekenstein?
Sorry?
How general you're talking about the Bekenstein entropy here? It's the same, right?
It's the same. It's the same as that. It's just I'm just putting in this extra thing of the entropy outside. That is what Bekenstein did. I'm not saying anything different from what Bekenstein did. He just defined this generalized entropy by associating. I mean, for the outside, we already knew that we have some entropy definition. The inside was that for the black hole, you associate this A over 4G, which is some entropy that's associated with the black hole, and somehow we define this collective quantity which satisfies all the laws of thermodynamics. This is just what Bekenstein did.
But then H bar appear in that 3/4.
Yeah, this is like, so I'm using natural units, so it's really A C cubed over 4G H bar. Maybe there's also K Boltzmann outside, but yeah.
It comes in the denominator.
Yeah, it's in the denominator. So it's a 1 over H bar effect.
So this is really a black hole related in the sense that
Yes.
you have a similar scenario involving HCG in some other context, but you don't really talk about anything unique about it. I'm talking about Chandrasekhar image. It's all. It has C, it has H cross, it's G. But we don't worry about any of those unique features, and we don't worry about quantum gravity effects and all that. So that's I always wondered, that's something to think of. You can go and look at the derivation of Chandrasekhar image exactly on this.
I see, but isn't it the case that if a star just exhausts its fuel, even
Doesn't
classically?
matter. That's the same as here too.
I mean, Fermi degeneracy is a quantum concept, if you mean that. To the extent that that is, yeah, and to the extent that's the effect. Is that what you mean?
Yeah, but it's also G there.
But you could just have had matter.
Yeah, right.
Yeah, sure.
If you just had classical gravity forming, like.
Just Fermi neutron. So you just have that I don't think proves that gravity is.
That's.
No, but
that's also similar.
it's a situation where G and H bar
We don't
come
worry
together.
about the quantum gravity effects there.
Yeah.
But I really think if you didn't quantize gravity, then you try to develop black hole thermodynamics as from microscopics, like we understand it from statistical mechanics.
Yeah.
I don't know if you could do it consistently because there's an H bar downstairs, and you could lose information by throwing in gravity waves. I mean, I don't.
Sorry, you mean in this situation where it's classical? Sorry, where gravity is classical? Is that what you mean?
I mean, you're putting a 1 over H bar in a black hole entropy, and not quantizing gravity.
Oh, and not quantizing.
Yeah. And I somehow think it won't be, it won't be consistent.
Yeah.
I don't have a front because anyway, okay, go ahead. But you could just do the matter and then.
I think what Babu was trying to say is just because the H bar appears, it could have come because of matter was quantum.
That's different.
I agree with you.
That's right.
The distinction is the horizon.
Yes.
You don't have horizon.
Yes.
We have it's nothing to do with matter. I can put an accretion disk on a black hole, and all those things. You should have something similar here. But the horizon, and we don't have that in the hydrox or neutrons.
Yes, that's right. That's right. I mean, and in those cases, like in principle, because you don't have a horizon, you could still associate the matter entropy with that object. In this case, like you could have all sorts of matter inside, but really what matters is the horizon. That's good. Okay. So now this quantity, the generalized entropy, is actually a very natural quantity. And it's sort of natural to group these terms together, the A over 4G and the entropy outside, which really you should think of as an entanglement entropy of all the matter fields outside the horizon, with everything that's inside. And in fact, Saskin and Aklam had pointed out that the separation between these two terms is sort of artificial. It depends on what your, every quantum field theory comes with a cutoff scale, and you can change your cutoff scale when you do the renormalization group flow. And by doing that, you can actually move terms from one to the other. So here's a cartoon picture for it. These green lines represent entanglement across this, between the region on the right and the region on the left. And I've sort of blown up the horizon because we're using some cutoff scale, say epsilon 1. So we can't really look at distances that are finer than epsilon 1. So the area you should think of as some function of this red blob here at the cutoff scale epsilon 1. But now let's say I course grain that system further. Then
I have one question.
Yes.
I understand this behaves like thermodynamic entropy. And it's not always clear that in all, let's say, situations which can be out of equilibrium, things are radiating and so on. Entanglement and thermodynamic entropy should behave in the same way.
That's right.
There's no particular proof that it should.
Yeah,
So
that's right.
why is, I understand saying it's the thermodynamic entropy or equivalent, but what is the immediate relation and saying that it should be the entanglement?
So what I'm saying here is just that the S out contribution is an entanglement entropy contribution between the interior and exterior. This whole thing need not be an entanglement entropy. This whole thing could be a coarse grained entropy, and so it's a thermodynamic. And this is clearer in some examples I can talk about later. But there are situations where we understand that this is not the entanglement entropy as you just suggested. All I'm saying is that from the bulk perspective, the thing that shows up here is the entanglement entropy in the between.
That isn't quite true, right? Because if you just go back to how the laws of black hole thermodynamics were formulated, S out is all the entropy, including
all the entropy just
it's
means
like how you apply the laws.
It depends on. So when I say entanglement entropy, I just mean I have some density matrix for the matter outside, and I just compute the von Neumann entropy of that. We often call that entanglement entropy. We can call it what we like, but it's just minus trace rho log rho of that exterior density matrix. This is also what Bekenstein would have done. I'm just specifying that, like when we include quantum corrections, it's like particularly clear that it's like an entanglement.
In a normal system, take away black holes and all this exotic. If we apply the laws of thermodynamics, then we have in mind entropy, which is not necessarily minus trace rho log rho. The fine.
Yeah, it could be a coarse-grained entropy in the sense that it's minus trace rho log rho for some coarse-grained rho. That could be. So you could have some fine state, but then, like, let's say you had some energy eigenstate, but you want to coarse grain over some ensemble. So then instead of that pure state, you would take something which is a mixed state, which is like a mixture over like nearby energy eigenstates. Then you take that rho and compute the entropy. That's the coarse grain entropy. So I'm just saying it's minus trace rho log rho for some rho.
So are you basically saying that the inside of the black hole is roughly like a bath, whether it's thermal or not, so that when you somehow integrate out those degrees of freedom, the full quantum state becomes a density matrix? Is that the way to think about this? Is what I was wondering.
It depends on the situation, but yes, like you can think of this as some entropy of some putative quantum gravity system.
But Pratik, all I was saying was if you took a gas in a box and you looked at some part of it and you looked at the other and you used thermodynamics and so on, then usually you don't mean a very fine-grained entropy there.
Yeah, so here we can do a little bit better. We can take the fine-grained entropy of the exterior matter fields, and then like this generalized entropy need not always have fine-grained interpretation. It could have a coarse-grained interpretation, but for the exterior stuff, we can be slightly finer, is what I'm saying. We could also coarse-grain the S-out stuff. That would be a even more coarse-grained thing.
And that would also meet all the laws of thermodynamics.
Yeah, it would. It would.
Because like Rajdeep's question, I mean, the essence here is that the black hole doesn't behave any differently from any other system, right?
That's true. But we can also take this more fine-grained perspective, and that has also helped us understand other things about quantum field theory and so on, which I might talk about. So here I'm taking this fine-grained stuff.
Initially start with this equation, which means first term is the black hole, second is the outside.
Yes.
Now we are saying entangled with this first with the black hole.
Right. So there is so let's say we have some description in the bulk where there's some region inside the black hole and some region outside the black hole, and there's some entanglement of the matter fields across
so
that.
what is the entangle here? This is the term. Initially you started with the S out in the outside.
Yes.
Now we are saying S out is also has an entangle.
I'm just saying that there's some pure. So let's say we had some pure state, which was of some matter fields which were entangled between the interior and the exterior. So then all I'm doing is looking at the reduced density matrix of the outside region and computing the entropy of that. That has an interpretation as an entanglement entropy with the interior.
Entanglement also included in S out.
In S out. That is S out. So S out is the entanglement entropy of these matter fields. And then there's some quantum gravity part, which is this A over 4G.
Sorry to go back to this, but let's say we compute your S gen. And you allow a black hole to evaporate for a long time.
Okay.
Will it satisfy the second law?
So it depends on
the context of this question, just to say, is that fine-grained entropy doesn't satisfy.
That's right.
Increase.
So it will not. That's right. In fact, like let's say you just had a black hole and you allowed it. I'll actually talk about this later. But the entropy of this S gen will actually go. Okay. It depends on which S gen we're talking about. But if we just did this thing where we were considering the fine-grained entropy outside, then we expect that it will eventually come down, because if we have a unitary theory of quantum gravity, then eventually the black hole is just gone, it's vanished, so A over 4G is 0, and we just have a lot of matter outside. We started with some pure states, so if it evolved unitarily, then we have a pure state, and so the entropy has to be 0. So it has to go up and then come down again. In a coarse-grained sense, if we did what you said, and if we coarse-grained this S out term, then it would keep going up. And that's what we expect from the thermodynamics.
But the black hole evaporation is only arising from an effective theory.
Yes.
So can we assume that and say that it will be eventually evaporation?
Yeah, because so the effective field theory, the validity of the effective field theory is set by.
Maybe a problem.
Well, it's the validity of this theory is set by basically how strong curvatures are in the background that we have. So, for example, this calculation of Hawking radiation basically just relies on the near horizon behavior. And the near horizon has a pretty, like we can take a huge black hole, which has a basically small curvature there. So we don't expect any quantum effects to be large. So perturbation theory should be trustable in that sense. And
So for the last point.
the last point we don't know. Yeah.
So there's no need for technically it can.
Yes, that's another thing that people call remnants. It's basically where the radiation just like it holds all the entropy till the last moment, and then suddenly with a burst it all comes out.
Because first we'll never observe at least the losses such for those. And
Right. Yeah, there are other issues with such things. For example, if they violate entropy bounds that I'll talk about, or people have also discussed how if you have such highly entropic objects which are of such small mass, then they can run in loops and spoil all sorts of QFT calculations. So it is a thing people do consider as an alternative. I don't subscribe to it, but yeah. Okay. Good. Okay, so what I was saying here was, okay, good. So the separation between area and entropy is a little bit artificial in the sense that if I now coarse grain a little bit more and I increase my cutoff scale to epsilon2, then I have this big blob and the area is just some function of this blob. And now what was here, entanglement between short range degrees of freedom is now all absorbed into the blob. So what was entanglement entropy is now part of what we call area. It's a non-trivial fact that when you change the renormalization group scale, this S-gen is actually invariant. And what happens is you move terms from one to the other. But it's a deep fact. Now, if you went the other way, instead of coarse graining, if you imagine going to finer and finer scales, then eventually you'd hope that everything is just an entropy, which has a fine-grained interpretation, and we don't have this area term anymore. And presumably that's what happens in the full quantum gravity field. Here I'm just talking about the low energy. What I was saying was, so here, like when we coarse grain, what we did was decrease the amount of entanglement entropy and increase the area. Let's say we go the other way, and we go to shorter and shorter scales. Then we can look at how this runs, and essentially you'll be increasing the amount of entanglement entropy and decreasing the area contribution, essentially because of running of Newton's constant. And eventually what will happen is A over 4G just becomes 0. I mean, that would be a possibility where everything just becomes an entanglement entropy and it would have a fine-grained interpretation.
So you have in mind that, let's say in string theory, you would have degrees of freedom strings on the horizon.
Something like that.
Giving rise to all the...
Yeah, so Saskian and Aklam proposed some sort of picture. It's been hard to make precise, but something of that sort. I think ADS-CFT also does something similar, which you shall talk about. But yeah, you want something where it's completely describable as a fine-grained entanglement, which would then explain why it has this thermodynamic interpretation. Okay, good. So anyway, the important point was that these two terms are very naturally, they go together. And so there's this connection between entanglement and geometry in the sense of area. They're like closely related and you can exchange one between the two terms. Another slide doesn't show up, so I'll just say it. Eventually, one would like to have a statistical explanation of such an entropy from an underlying theory of quantum gravity. That's what I'm saying. Okay. Good. So, okay. Good. So, this already suggests something deep about quantum gravity, which is the feature of holography. So, what's holography? We can ask, let's say you have a box of some size, we can ask how much entropy you can fit into this box. So let's say you have some sort of Dyson sphere or something, and you have some region of space that you have access to, and how much entropy that you can have in that region, which is visible to you. So let's say you just start with quantum field theory. You have degrees of freedom that scale like the volume. You can basically put a particle in this position, that position independently. You can have volumes worth of degrees of freedom. But as you add more and more degrees of freedom, they eventually collapse into a black hole. There's a limit to which you can do this. But once you have, these degrees of freedom collapse into a black hole, they're no more visible from the outside. And so if we follow Bekenstein's rule, we should associate an entropy with it, which is the area over 4G. Right? There's no more S out contribution from these degrees of freedom. So you thought that you were building up this entropy, which was scaling with the volume. But at some point, it just has to grow with the area, and it can't be larger than A over 4G, which is the size of your sphere.
Even QFT,
Yeah.
ground state at least, unless you put on a temperature,
Yeah.
the entanglement usually doesn't scale with the volume, right?
Yeah, but I mean, here I'm imagining that, so that's true, and there's some short distance scale with that. But here I'm just imagining, let's say you just had some isolated box where the stuff is not entangled with anything else, it's just the region of that system. Then in the vacuum or something, the entropy would just be zero.
Yeah.
So then we imagine increasing the temperature.
So there's a finite temperature.
There's a finite temperature effect, which is scaling with the volume.
Yeah, this is the thermodynamic entropy.
This is
going
The volume, so it's finite density. And
yeah, you can think of it as subtracting the vacuum entropy or something.
But I mean, in a gravitational system, the thermodynamic entropy will go like area.
Yeah, so that was the distinction between the finite and the thermodynamic.
So it has vastly fewer degrees. It's not just the entanglement, the full
Full possibility of
because
the size of the Hilbert spaces.
So the second law applies to thermodynamic entropy, and there you see that.
So for large boxes, the best we can really do is to just have a black hole which saturates that region. So it has an entropy of A/4G. Now this says that there's drastically fewer degrees of freedom than you might have thought. It doesn't scale with the volume, it scales with the area. And so it's sort of natural to think that maybe there's a theory which is sort of like a usual QFT, which has degrees of freedom scaling with the volume, but instead of living in the bulk, it lives on the boundary. It lives on the boundary of this region, which is this sort of hologram picture here. There's some hologram which is encoding everything that's happening inside the ball. And this is the holographic principle. It basically suggests that maybe quantum gravity is naturally formulated in one less dimension.
And this surface is the horizon.
Here I'm just imagining, take any box and imagine, like, that's the broadest form of the holographic principle. You imagine that you have some big region and then you do whatever you want inside that. And then the best you can do is have a horizon of that sense. Okay. So good. So now we said this holographic principle, and there's a very concrete realization of this holographic principle, which is ADS-CFT, which comes from string theory. And it's a precise duality of precisely that form that we said, where there's a quantum field theory living on the boundary of what's called anti-de Sitter space. The details of that are not so important, but it's basically some region of the bulk whose boundary has an actual quantum field theory living on it, which describes what's happening in the interior. So it's precisely a duality of this form, where it's clear that the degrees of freedom scale with the area and not with the volume.
As you know, Pratik, volume and area of ADS space scale in the same.
That's right. It's sort of a.
It's how clear is it?
Yeah, that's true. You could take this as just saying that this is something special to ADS.
No, but I mean, how good evidence is this that things scale like areas?
Things scale like area. Maybe it's not additional evidence, I guess. It's just a concrete realization of this idea of the holographic principle. I agree that it's not particularly strong evidence because the volume scales like the area. There's also slightly deformed versions of this, where like these T-bar theories, where you, instead of going all the way to the asymptotic boundary, you flow sort of to a region of space that's sort of in the middle at a finite distance. And then the volume and area are really different objects. So if we believe those sort of dualities, which are not on the same footing as this, then you would say that that's slightly better evidence of something like holographics. Yeah.
But actually, I mean, to go back to something you perhaps alluded to, if you looked at it from really far without taking the near horizon limit.
Yeah.
Okay.
Yeah.
Here, in a sense, if you take, sorry to be technical, but you've taken the full Lagrange geometry and taken the near horizon.
Yes. Yes.
But if I look at it from very far away, then you are realizing the holographic principle.
Yeah.
Because,
you think about it in flat space.
What was the horizon of the black hole, as seen from very far away, is replaced by some field theory living on a kind of stretched horizon.
Yeah.
So from that perspective, I think, I don't know what you feel, sure.
Okay, sounds good.
At least intuitive.
Yeah. Okay, good. So these sort of top-down approaches have given us like very precise micro-state counting interpretations of the generalized entropy that I just talked about.
Try with
No.
the arrow.
Try with the arrow, I think.
Okay. Does it show? No, it doesn't show. It shows up here, but it doesn't show up there.
So sorry about this.
I don't know why.
It's showing up at some point and then suddenly vanishes.
Yeah, I don't understand.
Right, without the presentation mode, just
Without.
just the maximally stretched
Yeah, I think
window.
that's.
Oh, I see.
Yeah.
I think this is
Yeah,
better.
I think this is better. It's
No,
okay.
it's
It's
just
okay.
hiding.
Oh, maybe it's because of the hide panel thing.
Yeah, so let's just keep it.
Okay, should we try
I don't
this?
think-
Oh,
But
wait.
you may not be able to go to it.
Select, yeah.
Okay.
Maybe.
Fine.
Hey, that's a lovely check.
No, he has all the hats.
Experiment also.
Okay. Good. So good. What I'd like to focus on here is a complementary bottom-up approach where we just want to understand the general principles behind quantum gravity by using these concrete models and seeing what we can what general lessons we can extract. And in particular, the approach that I'll focus on is this philosophy of it from qubit, which is this quantum information view of ADS-CFT, which basically uses information theoretic tools to try to understand quantum gravity. And the poster child of this sort of stuff is what's called the Ryuta-Kinagi formula, which tightens this connection between entanglement and geometry that I alluded to earlier, which says the following. It says that the entropy of a region R on the boundary theory is equal to the area of the extremal surface, gamma R, which is here, over 4G, plus the entropy, the von Neumann entropy of the bulk region, little r. This is precisely a generalization of the black hole entropy formula. It has exactly the same structure. And now it also has a fine-grained interpretation. So the generalized entropy of this region, little r in the bulk, actually has an interpretation as the entanglement entropy of the boundary theory in the region capital R. So it's almost exactly of the form that Bekenstein proposed.
So can you tell us a little bit about the validity of this? Is this correct? One loop or all loops? Or...
Yeah, so good. So at leading order, okay. So what I said here, so this was, so here I just talked about the classical extremal surface. In general, what you like to do is take the sum of these two objects and extremize that sum. That is at least valid to order 1, which is one loop. There have been claims that this should hold to all orders in perturbation theory, but I think that's a little under doubt because recently Akers and Pennington found that even at leading order, there can be violations of this formula. At leading order, for these kind of states called incompressible states. So these are not states that naturally arise from they're not very obviously natural states that you would write down in the bulk, but you could write them down. They're sort of these states where you have a mixture between a pure state and a mixed state of some sort, like which are very different from each other. And typically you would think of them as just living in different geometries altogether. But in those situations, you can show that there are violations of this formula even at leading order. So this formula is not sacrosanct. It's true whenever you have a given background geometry with perturbations on top of it, at least to order 1. And because of this issue at leading order, I suspect not to all orders in 1 over n, but there have been papers written about this, but I suspect that needs to be revisited.
Sorry, Can
Yes.
you please explain what is gamma or what is R and what
So R is just some boundary region. So this CFT that I talked about, the quantum field theory, is living on this boundary of this soup cap. So I just take that at a fixed time. So this boundary circle is just some fixed time. So it's a state at a given time of the quantum field theory. And now I'm looking at a sub-region of that. So let's say this was just a one-dimensional circle. Then this is some interval of that circle. And I'm looking at the reduced density matrix on that region and computing the von Neumann entropy of that region on the boundary theory.
So both these gamma and R are on the boundary.
No, so R is on the boundary. R is on the boundary. Gamma R is a bulk region, a bulk surface that extends into the bulk, which is anchored at the endpoints of R, capital R. And it has the property that it's basically the minimal surface. Basically the minimal surface anchored to that region. And then little r is the region between those two. So little r and gamma r are in the bulk, whereas capital R is on the boundary. So it's the von Neumann entropy of this boundary region, which is dual. So this is the boundary side and this is the bulk side. The bulk side, it's the generalized entropy of this region. That's the formula.
And the split between the gamma and the smaller, can you explain?
Sorry, which
The green region?
the green region is little r. So, yeah.
So how are you splitting this circle into the gamma or the smaller? Is it arbitrary?
No, so what I'm fixing to start with is capital R. So I start by fixing this interval capital R,
Right.
and then I find gamma R by looking for the extremal minimal surface, which is anchored to the endpoints of R.
It minimizes the area.
Minimizes the area.
The surface, which is like a soap bubble.
Right.
Yeah.
So specify the endpoint and minimize the area.
Right.
You choose that surface.
And then little r is just defined to be the region which is between those two surfaces, capital R and gamma R. Once I found gamma R, I can just look for this region, the bulk region, like it's a volume region between capital R and gamma R. So it's also bulk region.
Easy surface, the same surface, but in this case it's just line.
In this case it's a line. Yeah,
I mean the volume is the area.
Right.
Just sorry, not just slowing down, but if you're going to ask about going beyond classical and loops and so on, what is even the exact definition of this as an operator in the full quantum theory of gravity?
Sorry, the generalized entropy? I don't think so. I think the generalized entropy is some sort of, I mean, it's when you have like even approximate bulk description in terms of quantum field theory on top of some given geometry or so on, that kind of makes sense. It's not clear what it means.
Even a little more than that, when you have an approximate classical description. If you have huge quantum fluctuations,
that's right.
Quantum states which are
That's right.
classical,
Yeah.
where the variance
There's some kinds of, so you can have, for example, geometry states which are superpositions over different geometries, and those also you would have a formula which is similar to these.
where the interference terms are as big.
No, they're small. That's important.
What I'm saying.
Right. So if you have big interference terms, then you have nothing of this.
Correct. Exactly.
That's
So it can't be an exact formula.
It's not an exact formula. So the philosophy here is, when we have this low energy effective field theory, then we can make sense in these particular kinds of states which make sense within the effective theory. Then we can make sense of both of these terms. This is like a formula which holds then. And then we can try to do what I was saying earlier, which was decrease the scale, and then we have a better and better theory, but these terms become more and more fuzzy and it's not clear what they mean. But hopefully if you have a full theory, then you'd understand what they mean. But at this point, we don't understand what they mean.
So, just because I'm not clear, does that also become equivalent to close to Gaussian states? What you were?
Yeah, I think that's basically what it is.
Close to
Yeah, close to Gaussian.
Typically, that's the case.
Typically, there's a parameter which controls that, which is Yeah.
The big S of R is what?
It's the von Neumann entropy of the bulk region, the green region,
Enclosed by gamma R.
enclosed by gamma R and capital R. So between
So if I'm interested in some other entanglement entropy in the bulk,
like some
not
other.
necessarily enclosed by gamma R,
Yeah.
but by some other
Yeah,
region,
yeah.
How would I go about?
That's a good question. So I think it's not clear at this point at all what sort of surfaces we can. So the generalized entropy makes sense for all regions, right? We can associate any bulk region and compute the generalized entropy for that. We can also show, I think, roughly that it's a renormalization group invariant for the same reasons. But
Can I stop you there? Excuse me. You'd have to first define a region. In
that's right. So you have to first define something gauge
You
invariant.
say you can always associate, it's an imprecise statement.
No, I mean, so this is just a calculation. Yeah, in a given geometry. So if you just did quantum field theory on fixed curved spacetime, then you could try to compute this just as at a semi-classical level, not necessarily associating it to some non-perturbatively well-defined thing. So you could just define this quantity. It's a well-defined quantity.
So for general regions in the bulk, you're saying SGen can be defined?
Yeah, I mean, I just mean in the sense of
I see. So the other term also can
the other term. I'm just saying, like, if you just had some quantum field theory, then we just have on fixed background. That's all I'm saying. But SGen is quantum field theory on a fixed background because it's just
fluctuations have to be.
yeah, there's subtleties with gravitons. That's right. But that's right. So at this point, that's not a settled issue, but I think it's more of a technical issue than a conceptual issue. I think once you define things gauge invariantly, then it should work. I agree that it hasn't been settled completely, but In principle, you could define some sort of generalized entropy for these regions as long as you've defined it gauge invariantly. But it's not clear that there is necessarily a fine-grained interpretation to that entropy, just like there is for this. So for the thing that's enclosed by the extremal surface, it's like a very sharp, fine-grained definition, which is just the entanglement entropy of a boundary subregion. It could be that for other regions as well, there are such definitions, but we just don't know them. But I think we don't have good. So the only other example I know where we kind of have something like this is instead of having an extremal surface, if you have a marginally trapped surface, if you have the horizon of a black hole, then there's some sort of entropy you can associate to that, like the generalized entropy of that region, even if it's not an extremal surface. This is a construction by Engelhardt and Wall. But beyond that, one would really hope to associate some meaning to the generalized entropy of general regions, but I don't think we have anything better than this.
But could it be that this sum is somehow, for some technical reason, better defined when the surface has zero extrinsic limit?
Yeah, it could be. But so, for example, this marginally trapped case is a slightly better example where only one extrinsic curvature direction is zero, the other one is not. Still seems to be well defined. The arguments that went into proving renormalization group invariance don't seem to depend on it up to this subtlety of gravitons.
Right. It seems to me that there's a question you can only settle once you carefully understand
calculate what it is. Yeah. That's right. So I think people have been trying to do this.
Who are these people?
There is actually, so there's this postdoc at Berkeley, Sean Colin Ellerin, who's been trying to compute let me say this before. So Donnelly and Wall did a similar calculation for electromagnetism, where they tried to give it an interpretation and be careful about gauge invariance and all of that. So what he's been trying to do is try to do that calculation for gravitons to try to settle this issue. But at this point, I would say it's not settled, but
you feel that it's
I think as long as we're being careful about gauge invariance, then it should be okay.
Okay, thank you.
But that's my belief, but it's not a proof for anything. Okay, good. So fine. So this is a great example of the working of this generalized entropy and this connection between area and
I'm really sorry. There are so many questions, and maybe I can suggest that for the next 10 or 15 minutes, slow down on the questions.
Okay. How much time do I have? Like,
what is your
yeah.
I think we should go up to 12.
Where? So, oh my God. Okay.
Is that okay with you? So let's say 11:45.
Okay. I'll try.
I mean, if you extend beyond that, it's okay, but
I'll try.
We have not reached half of the slides.
That's right.
No, that's because we have been asking a lot of questions.
I like that, but
I think we should let him.
that's good. Yeah. Okay. Thanks so much. Good. So let me just quickly say, so this connection, this formula leads to another similar formula which says that the relative entropy between two states computed on the boundary region capital R is the same as the relative entropy in the bulk computed between two states in the region little r. Essentially, it says that if two states are distinguishable on little r in the bulk, then they are distinguishable on capital R on the boundary, and vice versa. This is what's called the JLMS formula. And this leads to this idea of subregion duality. So it says that there's a fine-grained map which tells you which region of the bulk is encoded on which boundary region. So little r is encoded, all the information about little r is captured on capital R. And this is true for any general RD surface. So this is a little bit better than what we knew before. What we knew before was ADS equals CFT. So everything in ADS equals everything on the CFT. This is a slightly better version of it, which says everything in little r equals everything is captured in capital R. Okay. Good. And this thing can be well understood just by abstractly thinking of ADS CFT as functioning as a quantum error correcting code. So let me just say a little bit about what that means. So the idea is that semi-classical states in the bulk are encoded redundantly on the boundary CFT. So the picture is usually this. Let's say I have three regions A, B, and C, and I want to reconstruct the region capital, the operator which is sitting in the center, which is O. Then if I take the union, if I take any of these regions A, B, or C, O lies outside the RT surfaces, which are these respective surfaces. And so none of the regions A, B, or C have information of what's happening at O. On the other hand, if I take the union of A and B, then the RT surface is basically this surface, And so O is contained in the union of A and B. It's also contained in the union of A and C or B and C. So it's a funny situation where none of the individual regions have access to the information about O, but still any two of them put together do. And this is exactly how quantum error correcting code works. So in a quantum error correcting code, what happens is you have some redundant encoding of the bulk information onto the boundary legs. It essentially takes this form where there's some entanglement between, so let's say I just take A and its complement. Then there's some entanglement, extra entanglement degrees of freedom, which are called chi, along with the information. So here, let's say we have little a is the entanglement wedge, or basically the green region for capital A. And A bar is its complement. So let's say we had some state in the bulk, which is I on region little a and J on region A bar. Then the encoding on the boundary is of the following form. There's some unitaries acting on them, which put it in the form I on a subfactor of A, J on a subfactor of A bar, and some extra entanglement. This entanglement is important in order to have this redundant description. So this was specifically what I wrote for the split into A and BC, but you could write a similar formula for a split into B and AC or C and AB, any of them. But the entanglement is crucial for the existence of such a code.
And the entanglement can be different for different encoding.
It could, yeah, that's right. Sorry, different encoding, different region, different regions. Yeah, different regions. In fact, basically what you said, you can show that any exact quantum error correcting code which has this property of subregion duality has some analog of the RT formula. And the RT formula, in the RT formula, the entropy of this, the entanglement entropy of this chi is exactly the thing that plays the role of the area. So as you said, like for different regions, you can have different chi because you can have different areas. And it's a, yes.
One more question.
Yeah.
So let's say I have excitation in the C region, the bulk C region.
Yeah.
XC,
Yeah.
IC.
Yeah.
Now that you can draw the circuit saying that is encoded in the BC and not A.
Yes.
Right? You can draw that circuit. You
Yes.
also draw a circuit which says that it's encoded in AC and not B.
Yes.
Is there a circuit which makes both of these things manifest?
No, because there's different unitaries you need to apply. So this encoding thing depends on the region, right? So this UA and UA bar. So we act with some UBC, which is not a product. So it's like it entangles them and it basically disentangles them. And so UBC will be different from UAC, will be different from UAB. And so if I first do, let's say I act with UBC, and I've separated the information, then like I basically, it's clear from the fact that if I act on BC and extract the information of, I have a choice. I can extract the information of O either onto B or onto C, for example. I mean, in a simple example. And once I've done that, then now, suppose I've extracted the information onto B, then there's no way I can get it onto AC, right? Like with that unitary. So then there's no, yeah. So there's no way to make
the fact that we can do it in this all different ways for the same operator.
Yeah.
Does that leave certain restrictions on this kind of chi's and so on?
It doesn't. Good. So it doesn't. All it needs is the state has to have this form.
Yes.
When you try to put things together, yes, there are some restrictions. It's non-trivial to build a quantum error correcting code. So you need to have compatibility between different things. But all it says is that it just takes this form. And so at this point, we can just say gravity ADS-CFT basically works like a pretty general quantum error correcting code, which has this property of subregion duality. Later, I'll say that for gravity, there's actually something more special about chi, which is not true for general quantum error correcting.
What is chi?
Oh, chi is just, so okay, in this language, it's just some redundancy. So in this case, we have some semi-classical states Ij, right? So we're encoding all of that into the larger system, which is the boundary. And then there's some redundant piece remaining. So
I mean, there's more than the boundary?
Yeah.
Why is there more than
there's more in the boundary, you said?
more than the boundary?
No, it's more in the boundary. So I'm saying less than the boundary.
Sorry, I didn't understand. So
This is the bulk.
A and A bar together make up the whole boundary, right?
Capital A and capital A bar.
So then what's left?
No, this is, so A1 is some subfactor of A and A2 is some other subfactor. All of this together is the full boundary.
Sorry, I thought A and A bar together make up the whole boundary.
Yeah, so this is A1, which is A1 times A2 is A.
So A1 and A1 bar don't make up the whole boundary.
No, A1 times A1 and A2 together are A, A1 bar and A2 bar together are A bar. So this whole thing together makes the whole boundary.
Okay,
That's what I mean.
thank you.
Okay.
And then just to say that chi, if I understand right, the entanglement in chi, in a sense, is the area.
It's exactly that. Yeah, that's right. So this chi on the boundary is exactly what we mean by area on the boundary. And this is also in one-to-one correspondence with this GLMS formula that I told you, which says that the relative entropy in the bulk is equal to the relative entropy on the boundary. Good. So this is telling you somewhat what the mechanism of this encoding of the bulk onto the boundary is. And there's a particular toy model which is tensor networks. Tensor networks have been used a lot. I mean, they started from the condensed matter community in order to understand a description of states where the entanglement properties are pretty manifest. And in particular, there's a model called the random tensor network, which is a great toy model for holography. And similar models called random unitary circuits have been used in quantum information and condensed matter for understanding thermalization and chaos and so on. So it's a tool which is pretty widespreadly used. And so what are these random tensor networks? Basically, let's say I give you any graph, which has some set of edges and vertices. Then you can define a boundary state by picking hard random states at every vertex. So there's some random state at each vertex. And then we project those states onto maximally entangled Bell states, which connect the edges. Right? So there's random states at the vertex and then maximal entanglement between things connected by an edge. That's the construction. And in this case, we can think of, so that it does satisfy something that's analogous to the RT formula, which is if I compute the entropy of these boundary legs, it's given by the minimal cut through the graph, which is anchored to the endpoints of this region, plus the bulk entropy in this region written up. So it's almost exactly like the RT formula.
I'm not supposed to ask any questions, but I'll ask you when you. No, you're right. I'm sorry, but you can answer later.
Yeah.
People draw these pictures, right? Is this supposed to be a discretization of the bulk? Is it a?
It's
what is it?
We can think of it as some qualitative picture of the bulk. I don't think we should think of it as necessary. Well, I guess roughly, if you did discretize the bulk and associated some degrees of freedom with each region, then it's roughly like that. Yeah. But you shouldn't think of it as some fine-grained lattice of the bulk or something. It's not the complete description. It's just some effective description.
I mean, is it a description or it's some cartoon?
Okay, good. So that's at this point, what all I'm going to use is that it's a qualitative thing. There's a qualitative connection between this picture that we have for the bulk and ADCT. And there's some ways in which you can sharpen that connection, but broadly, I would say it's a qualitative connection.
Okay. So just to ask, so broadly, you use it as a qualitative connection and draw some inferences which you might then be able to test in a precise way.
So the whole philosophy of this talk is going to be take these pictures seriously. These are tractable models. We can compute things in these models pretty effectively and sort of hope that those lessons that you can extract from this carry over to the more sophisticated model, which is ADCT or gravity. And in many, many situations, we learn that does happen. That's the lesson.
Thank you.
Yes.
And more than the fact that you are going to put random tensor network, what makes it solvable,
right?
Would make it very hard to get that answer directly to any particular geometry or anything.
That's right. So this randomness is probably just an effective, like coarse-grained description. One might just say, yes, we're doing this. It's exactly the same. It's exactly the same. So you're just
what Hamiltonian there
right. You're just modeling some Hamiltonian, and you hope that it's a typical Hamiltonian. So whatever you learn from this is like applicable to whatever that Hamiltonian. It's basically the same.
So random here means what?
Random
structure is arbitrary.
Sorry,
is V structure?
The V is like a random state. So you're basically averaging with a random unitary. You start with some fixed state and then average it with a random unitary. So you do one instance, compute the entropy, then you do it again, and you basically average over the entropy over all of these instances.
I think there are models where these tensors are taken to be fixed, right?
Yes.
Why do you like those? I mean, in terms of reproducing the various properties?
They don't. So I think you mean the stabilizer tensor network, sort of like happy model
tensors.
Yeah. So those models are, I think, not as good as this. There's particular things that I'll talk about which this does better than that. One thing which it does better is that, which I'll just say on the next slide actually, is that this works as an approximate quantum error correcting code. Everything I told you before this was that it was an exact quantum error correcting code. There are important qualitative differences that happen in going from exact quantum error correcting codes to approximate quantum error correcting codes, which are important for certain things that we learn. So that's one aspect. The other thing is it's pretty natural here. So in many of these models, there's just some small, like, I don't know, 5-dimensional bell pair that's connecting them or something like that, which is a little unnatural in this sense, because here we want the area to be something that's a large quantity. And so in this case, what we normally work with situations where the edges connecting these vertices have a large bond dimension. That's the situation where this is a tractable limit. It's much more naturally connected to gravity. So one thing to note is that, again, like going with this connection between entanglement and geometry, the role of geometry here, where geometry here just meant the minimal cut through the graph, the role of geometry is literally played by entanglement. Entanglement between the bell pair that's connecting the two vertices. It's a good manifestation. Okay. But apart from just being this toy model, it's actually a pretty good toy model in the sense that they exhibit all of the previous properties that I said, the RT formula, the JLMS formula, subregion duality.
Sorry.
Yes.
So you dream these vertices,
Yeah.
and then the edges are also random, right?
The edges are, no, they're like fixed bell pair states. You don't need to add randomness to that. But
If you go back to this previous this thing, I could have connected them in other ways also.
yes, that's right. So you could connect them with non-maximally entangled legs, for example.
This is the maximum. I see. Okay.
Yeah, that's right. There's reasons why this will turn out to be more accurately describing gravity. Okay, good. So as I was saying before, there are these random tensor networks that approximate quantum error correcting codes, not exact quantum error correcting codes. This is actually important because we expect this approximateness to automatically show up in gravity because of non-perturbative effects. In particular, one example of this is, let's say we have a region which I take to be the union of these two intervals. Then there are two RT surfaces, two candidate RT surfaces, one which is this green surface, which is the disconnected surface, and one which is the orange surface, which is the connected surface. You can imagine changing the entropy of the matter which is in between these surfaces to shift which one is the minimal surface. So you can basically, by changing the state, you can change which one is the correct RT surface. This is something that's only possible in approximate quantum error correcting codes. You can't have these phase transitions happening in exact quantum error correcting codes. And it's important that this has this problem.
So you say it's approximate, there's some fidelity vis-a-vis.
Yes. So basically what happens is that it's the dimension. So there's the dimension of the bell pairs that's being contracted. That's some parameter d. If we take that to infinity, that's when this becomes an exact, like, very sharp code. But the errors are connected by powers of d, essentially. 1 over d.
And if you, in the qualitative map to gravity, you would say that this bond dimension is like 1 over g Newton.
D is like e to the 1 over g. Because log d is like the entropy. Log d is like a over g.
Thank you.
Okay, good. So the question is, how much can we learn from this toy model, and how far can we push the limits of this qualitative connection between tensor networks and gravity? Can we learn something? Good. So in order to do that, there's a first order tension that arises, which is we computed the entanglement entropy and showed that it has this property that it satisfies an RT formula. But there's a very simple generalization of the entanglement entropy, which are these Renyi entropies. Renyi entropy is defined as basically 1 over 1 minus n log trace rho to the n. So it's a generalization which gives the entanglement entropy in the limit n goes to 1. So it's a 1 parameter generalization of the von Neumann entropy. And you can compute this. And in the tensor network, it turns out that this object is independent of n. So no matter what n is, you get the same answer, which is just the log b for the minimal cut. However, it can go from like 0 to infinity.
One.
So when n goes to 1, you have to take a limit because trace rho is also 1. So log of that is 0. So it's a 0 over 0. When you take the limit, it becomes minus trace rho log rho, which is the one Neumann. Okay.
This thing is independent of n. So I could all along work with the one Neumann.
In this model, not in general, in this model, it turns out to be independent of n. Yeah. But in gravity, there have been calculations which have been done which showed that it actually depends non-trivially on n. And there's a general rule that was proposed in these papers, which essentially says that the gravity dual of Renyi entropy is given by deforming the geometry in a certain way and then computing the area. So you compute the area again, it's still like a Ryuta-Kinagi formula, but it's in a different geometry, which is changed in some very specific way. And the problem is the random tensor network lacks this equivalent dynamical response. There's no form in which you deform the geometry just stays the same, and you still compute the entropy in the same geometry. That's the difference between gravity and tensor network.
So the deformed geometry is the deformation due to the multi-sheeted boundary.
Yes, basically.
Yeah.
That's partly why I was asking. You must go on, but if it were an honest to goodness, even discretization, then it would have responded to the changes in it. You know.
That's right. So I'm going to say something which does better geometry.
Okay. But this
we
is
can talk
not
about
that. You know, you just lay down regard. It's not like you're trying to tessellate a geometry. Some
At a very coarse level, I think you are tessellating geometry, and it will do that job. So let me just say what.
I'm sorry.
What is the point with the respondency changing?
The geometry. You know,
Like suppose it was an honest
space. And as we change the system, it should change. That's right. But it's not even doing that.
Yeah. Good. So there's this difference between the tensor networks and gravity. So how can we bridge this gap? So the question is, what can we do to resolve this tension? And the important thing is to realize that in gravity, there are also states of exactly this form. So the states which were considered earlier in the proposal that I told you were states where the geometry does respond to the insertion of this this deformation of the geometry. But there are states which do have a flat entanglement spectrum, and they do not respond to this deformation. These are what are called fixed area states. These fixed area states are approximate eigenstates of the area in the sense that they are very sharply peaked at given values of the area. Unlike geometries that we usually consider, which are more like coherent states. So the normal states that we consider, which are semi-classical states, are essentially coherent states, Gaussian states, as you're saying. And those coherent states would be like Gaussians, which are reasonably wide. They have some width of order square root g Newton in the area, and similarly in its conjugate derivative. But we can instead consider gravitational states where it's sharper. So these are more like position eigenstates instead of coherent states. Those states, analogous to position eigenstates in quantum mechanics, will be highly non-classical, right? Because you've sharpened it in one variable, it's very spread out in the conjugate variable. So it's similar to how the wave function of an eigenstate spreads out very fast. But they're useful as a basis. So position eigenstates are still useful as a basis to do calculations. And so that's sort of the philosophy here. We're trying to use these fixed area states as basis to do calculations for general states, which we may care about, say coherent states, which are semi-classical.
They might be very high energy, right?
They aren't necessarily high energy. So for one simple example of this is, for example, let's say take a black hole. A black hole horizon also has area fluctuations of this sort in the thermal ensemble. In the canonical ensemble. And the analog of this would be going to the microcanonical ensemble. So you just fix the area by fixing the energy to a small window. That's not a very high energy state, but it has exactly this property. It'll have a flat entanglement spectrum.
But I mean, if you squeeze down the uncertainty from what is it, 1 over root g Newton?
Yes.
Is that right?
The area has a width of order square root g.
Square root of g Newton, yeah. And you want to squeeze it down to much smaller, right?
Yeah, let's say parametric like g to the 100 or something.
And you say that you can do that with a fixed energy and it's not a very singular thing.
Yeah, it's essentially because It's essentially because it's at the horizon. So you're adding large amounts of energy at the horizon doesn't really affect the ADM energy much. It's roughly because of that.
Sorry, I shouldn't have said.
So here for area, you mean the area of the artist.
I mean the area, yeah.
So this state is defined with respect to the region that is specified.
Yes, that's right. Yes, that's right. Okay, good. Good. So with this, we learn that the RTN, the random tensor network, is modeling this fixed area basis, which is of these position eigenstate like gravitational states.
But then this will work only for that region, right?
It will work only for that region.
But
So I'm
produce
not necessarily. So that's what I'm going to say. So that's a limitation of what I'm saying, because this only works when you have a particular region, and a little bit more generalization of that is if you have a family of nested regions, so that the RT surfaces are all space-like separated. This doesn't work when you have crossing regions. So when you have regions where the RT surfaces could be time-like separated or they can cross and so on, this will not necessarily work unless you have some special like time-independent geometry or something like that. The general case where it works is when you have one region or a family of nested regions.
No, I mean, even if you have one region, now I change that region and ask another entanglement entropy question.
You
then it
would,
will not work.
right. So
Not
this
necessarily
fixed area state will not work for another region. That's right. But then you would want to construct a state for that region, and that would be the analogous state.
Yeah.
So I'm not saying so. This only
But
partially.
on the other hand,
Right. So the random tensor network does much more than this. So this only partially relieves the tension between them. It doesn't completely, and that's probably fine. Okay. It's just a question of how much you can make them similar, like how similar they could potentially. So essentially, this basis, I mean, now once you have a basis, then you can take a superposition between different such tensor networks, and that would essentially look or behave like these coherent states, which have appropriate fluctuations.
So it's 10 minutes, and then the committee has a hard deadline at 12. Leave 5 minutes for questions. I feel that's more important.
Okay. I'm going to try to wrap up. I have to basically skip half,
Yeah.
but okay. Fine. Okay. So we have these coherent states with by using this basis. And this will essentially reproduce the end-dependent ready entropies. The reason being, we have these different geometries. So let's say we just have a superposition between two such tensor networks. The minimal cut here is these 3 legs, and the minimal cut here is these 2 legs. If you have a superposition, what can happen when you compute the ready entropy is that the dominant saddle can shift from one to the other, thus changing the area and thus changing the entropy. That's essentially the mechanism by which gravity works. It's a superposition over these fixed area states. And that's how it's doing this dynamical response. So what, with regards to what you were saying, like we can do this discretization by taking a superposition over them. And that would be a better model of what gravity is.
I see. And then if you can superpose so that you get the kind of widths you like.
Yes, yeah. So it's I mean, the gravity will tell you what these probability weights have to be to reproduce the states that you like. Okay, fine. Fine. Okay, so what this essentially says, so earlier we learned that
It's up to you. If you'd like, to continue, well, we can have questions after you send it. But up to you.
Okay.
Yeah.
Okay. Yeah. So earlier we learned that in an exact quantum error, any general exact quantum error correcting code had this property that it had an RT formula, it had a GLMS formula, and it had subregion duality all consistent with each other. Right? Any one of them implies the other. But now we learn something more special, and just by abstractly working with this, you can actually show that in order to reproduce the Renyi entropies in gravity, there's a special property, which is that this chi, the state that I talked about before, has to be maximally entangled. So it's exactly these bell pair-like states which the random tensor network has, and that's why it was modeling it better instead of considering some non-maximally entangled state. Yeah, so just say that. Okay, so let me just briefly. Maybe I'll skip over this actually. Okay.
That's what the mind plans.
Sorry? Let me keep it a magic note. Okay, so roughly why this works out is essentially this basic fact that when we average over Haar random unitaries, the average is equal to a sum over permutation. So when you take many copies of these Haar random unitaries and average over them, the only things that survive that averaging is a sum over permutations. Hopefully, I mean, if you work with any of these circuits or something, it must be familiar. And there's a precise match between the fixed area geometries. So if I take like 9 copies of my geometry and glue them in particular ways dictated by this permutation, there's an exact match between the geometries and the terms that I get from this Haar random averaging. And there's a precise connection between these, not just the leading term, but this whole sequence of non-perturbatively suppressed terms, all of them match. So that's sort of the mechanism behind why the random tensor network is doing a decent job of reproducing what gravity is doing, as long as you're using fixed area states. In recent years, we've seen a sort of a resurgence in the use of Euclidean gravity techniques. So Euclidean gravity is this, I don't know how much to say about it, but it's essentially trying to do the Euclidean path integral version of QFT, right, but for gravity. But
You continue.
okay, sorry. And it's a bit of a black box, like we don't exactly understand what the rules are in that context and so on. Here, what we've done is essentially translate all of these things just because of this connection between the gravitational saddles that we obtained using fixed area with the tensor network. It's sort of a Lorentzian version of what we were doing. So everything that has some Euclidean interpretation has a complementary Lorentzian interpretation using this tensor network. It's basically just doing the same calculation in two different ways. Okay, so okay, let me just briefly mention one application, and then just yeah. So the application is going to be the page curve of black hole evaporation. So as is well known, a black hole evaporates into radiation, which apparently loses information of how it was formed. This is basically the black hole information puzzle of Hawking. It's the fact that there are entangled pairs of radiation, one which goes into the interior, one which goes into the exterior, the black hole eventually vanishes, and the area keeps shrinking. Now, the state of this radiation outside is essentially thermal. It doesn't depend on what the state was that you started with. So this was the puzzle. The puzzle was, where did all that information go? Why did the entropy become non-zero? And in a unitary theory in particular, you would want some mechanism by which all of this information should come out eventually. But this seems hard to do while simultaneously having a semi-classical description of the horizon, in particular because entanglement across any region is sort of universal. When you look at any region across a cut at short distance scales, it's entangled in a pretty universal way. So if you want to change this thermal radiation, it must ruin the entanglement across the horizon at some point. And that's what people call a firewall. This firewall basically says, oh, you can get out all the information as long as you don't have an interior, you just have some object there which you can't fall into and so on. It's not described by general relativity. And some drastic change to general relativity because it's in a situation where there are low curvatures. There is nothing special happening at the horizon, but still it's like a drastic failure. And so for a long time, it was believed that in order to see the mechanism by which all of this information is coming out, you really need a full quantum gravity theory in order to even compute how the entropy is going up and coming down again. Now, the entanglement entropy of a black hole, as it should be in a unitary quantum theory, was estimated by Page in 1993. And he essentially did what you could think of in hindsight as a tensor network calculation. It's the calculation of the entropy of a random bipartite state with different number of degrees of freedom on either side. It's just how the entropy behaves as a function of how many degrees of freedom you have. So we can essentially redraw his calculation in a suggestive way. So if we think about just taking the radiation of the black hole and combing it all out into some box, we separate out all of these degrees of freedom, then there's an effective tensor network which describes this. This is now a tensor network, which is slightly different from what Page did, but is essentially the same. There's some radiation which is entangled, so that's these green legs. So the green leg here is so this side is the box of radiation, which is entangled by these green legs. It goes into some sort of black box. There's some tensor that I'm drawing, which is representing the geometry, whose end is the black hole horizon. So this red surface is the horizon area of this black hole. And then there's some other tensor which maps that state onto the boundary state. So this is basically a simple version of the random tensor network that I drew previously. Now in this case, this is basically the same as what Page did. In this case, if you compute the entropy of the right-hand side, the minimal cut is either going to be at the horizon or it's going to be these green legs, depending on where you are. So at early times, when you have small amounts of radiation, the minimal cut is these green legs. So you get the radiation entropy. But at late times, you get the area of the black hole. And at late times, you have a large amount of entanglement with the interior. In this random tensor network, there's really no distinction between entanglement and area, as we mentioned before. And so there's going to be a phase transition in the Ryu-Takanagi surface. The surface shifts from being at the green legs to the horizon. Now, precisely this turns out to work out for the actual gravitational calculation. There's true gravitational instantons called replica wormholes, which were discovered, which explained exactly this page curve using semi-classical gravity. So what ends up happening is essentially the same mechanism gives you a shift in the Ryu-Takanagi surface such that the entropy goes up and then comes down again because it shifts from the radiation to the black hole horizon. And this is remarkable because for a long time we just thought you needed a full quantum gravity theory in order to even see this happen. But this is a purely semi-classical description. We just got it from a gravitational instanton. It's pretty remarkable that the Euclidean gravity even knew how to recover this page curve.
Did the random tensor network play a role in this way of thinking?
I'd argue that it did. I mean, this becomes more of a, what do you call it?
In the paper,
sociological
question. Do the papers that do they mention random tensor networks as their motivation?
So PSSY in particular is one where they did mention this thing. So it's actually more finer stuff. Like for example, not just the page curve itself, but the smoothening out of the page curve and stuff. The calculation is pretty analogous to the random tensor network. So they mentioned this in an appendix because it's sort of what led them there. But this is a sociological question. I don't want to make a claim on this. But maybe one way to say this is you could imagine a different history where Page just took this calculation really seriously and just discovered. I mean, suppose in 1993, Page knew about the connection between fixed area states and random tensor networks. He could just have found this instant. That's sort of a provocative way of saying it, I guess. Good. So, and this is remarkable, but it's still, all it is just an entanglement phase transition. As we said, like there are much simpler examples where we have this entanglement phase transition, like in the two intervals example, like we just jump from one surface to the other, and it's exactly just that. And in a general such transition, you can compute what the corrections even to the page curve are just by decomposing it into these fixed area states and using the tensor network calculation. So you can get there's sort of a universal order 1 over square root g smoothing out of the page curve at the tip of the page curve. And you can get it just from this calculation, just by decomposing it into these fixed area states. So that's one application. I wanted to mention a few more applications, but I'll just briefly run through them just to emphasize that there are applications of this thing.
One small question.
Yeah.
So in Page's calculation, it's not quite random tensor that were used, right? It's just the random state.
A random state is the same as a random tensor. Like there's no difference.
Came with a lot of structure, right?
It did, but I'm just saying it's like the dumb tensor network where it's one vertex and like just the legs that you have. It doesn't have a structure. Like it's the simplest graph that you can write down. It's just one vertex.
Yeah, but okay, fine.
Okay. Anyway, you need to go on, but I mean, we could just say what Page was doing is true for any generic state.
That is true. That's absolutely true.
And therefore, is the random tensor network going to capture what happens for a generic system? I don't think so.
So you mean a non-gravitational system?
No, I'm only interested in gravity.
Okay.
So the question is, for a generic state, which you get out of gravity, maybe interacting with semi-classical radiation, is the random tensor network actually capturing the behavior for a typical generic state? This is, I presume, the version of the random tensor network, which sums over different tensor networks.
So when you say generic state, does it have a semi-classical geometry?
Yes.
Yeah, then I think the discretization of that geometry into this tensor network does have that property.
I mean, you presumably are summing over random tensor networks here, right?
For this part, yes. Just to get the fact that it goes up and down again, you don't need that.
Yeah, so that already tells you that it's, it's not even a very, I mean, that version of random tensor networks captures very little about gravity. Right? Okay, let's have the discussion later.
I agree. But I'm just saying, okay, if you want, we can take a superposition, which is like just exactly the same state that you like, and then compute it using that. then you're not using literally the random tensor network calculation, but it's like a decomposition into this fixed area state basis and then computing it. It's still a random tensor network calculation, and that will give you this refined base curve, like for any state that you like.
This kind of correction you're talking about, base curve. Base curve is known from the class.
Yes.
Is that being computed by string theorists and others, or
this thing? You mean from a full quantum gravity theory?
each other? Yeah. I mean, as a correction, is it possible to make comparison with other calculations?
Well, so that's the thing. So this order 1 square root G correction comes from this Euclidean gravity calculation. So you can do a Euclidean gravity calculation which shows you exactly this form. I don't think we have enough control to do it in the full quantum gravity theory.
Even in the Ashley kind of we're trying to do some of these correction to page curve.
Yeah, I don't know about that. But this is a pretty general thing. So for example, so this order 1 over square root G correction is very closely related to something that was found in the condensed matter literature, which is order square root volume corrections in these high energy eigenstates. They have a very similar behavior. And it was found by Shednicki and collaborators. So this is a version of that. So it is true that there are these corrections in general systems. This is like the version of that for gravity.
So if you have two saddle points and you sum them, is that what's going on here?
No, that won't happen. So you need, apart from those sums, the problem is, so you have these two saddle points. If you take the sum, you get nonsensical answers because there's actually interpolating saddles between them. The tensor network has these things called the non-crossing permutations, which lie between. So in the tensor network, the choice of saddle is basically a choice of permutation. Right? So there's two permutations: the identity permutation and the cyclic permutation. Those are the two saddles that you like. Now, there's many permutations that lie in between them in a very precise sense, and you need to sum over all of them in order to recover this.
It's like the short string, long string story. Of ADS. Okay, I see. So it makes predictions for new saddles in gravity.
Yes, and I can find them. Maybe I had that picture before. So I have the picture.
It's fine.
It's this picture. So it's basically this sort of a saddle. It's something that wasn't considered before, and it's exactly this. So if you look at PSSY, for example, precisely this sort of. I mean, it's hard to construct these saddles except in very simple models like JT gravity. In those, you can exactly construct the saddle, and it's important for summing and getting the picture.
Thank you.
Good. Okay. Yeah. Okay. Good. So that's one example. And then there's many such examples. So I won't go into all the details. I'll just mention what other things this has been applied to very briefly. Let me skip this. So the first thing that has been applied to is Renyi entropy. So Renyi entropy is a natural generalization of entanglement entropy, as I just said. As I told you before, there's this formula that was written down, which was to deform the geometry in a certain way and then compute the area. And when I told you that, I was actually lying because it turns out that formula is not quite correct. This will be discussed in my technical talk, so I won't go into the details right now. But that formula is actually wrong. And you can find corrections to that formula using this idea of decomposing states into fixed area states. That's what I'll mention. So that gives a more complete answer for the Renyi entropy in this context. The entanglement negativity is, so what we discussed before was measures of entanglement between pure states. So if you have two parties in a pure state, then the entanglement entropy or Renyi entropy captures the amount of entanglement between them. But if you have mixed states, then you need some other quantities because these entanglement entropy and Renyi entropies capture classical correlations in addition to quantum entanglement. The one such quantity which does actually capture quantum entanglement is entanglement negativity. And the holographic dual of this, the gravity dual of this, was controversial for a long time. But using this idea, we've been able to settle down what the gravity dual is. I won't say much more about it, but this is another application.
So just to say the gravity dual for entropy negative.
Entanglement negative. Yeah. We can talk about this offline. There's another application of this, there's a quantity called the reflected entropy, which was essentially written down to compute what's called the entanglement wedge cross section. So the cross section is this surface, which splits the entanglement wedge into two parts if you have two parties A and B. So just like the RT formula, people wanted to write down a quantity which computes the area of this surface. And this reflected entropy was an entanglement measure which was written down to compute this. But it was very hard to prove from the gravity side that this was the correct tool. So a lot of input came from the random tensor network calculation, which was able to fix this issue. Because in the random tensor network, firstly, it's more tractable. And you can have other techniques such as numerics and quantum information techniques and so on to actually nail down that the cross section is exactly the dual of this one. This has implications. In particular, you can prove that holographic states have large amount of tripartite entanglement. It sort of refutes this earlier conjecture which said that holographic states need only bipartite entanglement. So it has applications of that sort. There's another quantity of this sort called the entanglement of purification, which is notoriously hard to compute because you have to optimize over all possible purifications of a system. And it's almost impossible to compute for anything except the bell pair. It so happens that for tensor networks, we were able to prove this, compute it, and prove that it's actually equal to the cross-section for certain class of tensor networks, which is, I think, pretty remarkable that you could ever even compute something like this. Okay, so with that,
the last 2-3 things were using tensor networks, not necessary, but then you can translate everything you said into gravity using your fixed areas.
Yes, that's right. That's exactly right. There's a similar story for relative entropy. I told you about the JLMS formula. Again, I was lying. There's corrections to that. We can fix that. Okay, good. So let me just summarize. We learned that Euclidean gravity has given us a lot. For example, the page curve, which it's probably way more than we expected. And this connection between fixed area states and tensor networks has been useful to understand it better. It's a more tractable version where we can do calculations and then try to apply those ideas to gravity and see how to get things out of it.
Sorry, so everything that comes from the tensor network can be translated to gravity?
Not everything. You have to be a little careful, as I was saying earlier. Like, for example, when you have situations where surfaces cross and stuff, there can be not an exact match. But essentially, when you have the thing, that's the situation where it becomes subtle. But when you have things where the only relevant surfaces are all space-like separated from each other, then usually works out fine. But you have to be careful each time.
Usually there's just statements like saddle points map.
Yes.
Saddle points.
Yes, that's right. That's exactly where the magic lies, is map between the saddle points. Yes. That's right. Okay, good. My general philosophy about this is that I'd like to go beyond ADS-CFT and try to understand things more generally, not just in anti-de Sitter space, maybe in our cosmology or in flat space or other geometries. And the ideas from quantum information theory are sort of universal, and tensor networks you can write down with whatever geometry you like. So my hope is that by using these ideas, maybe we can go beyond and just extract the universal lessons and apply it to different situations. That's the broad scope of things. There's still a lot of open questions. In particular, one thing that I'll mention is when I talked about the page curve, we talked about the situation where we take all the radiation and put it in a box. Secretly, what I meant is that box is non-gravitational. So we removed it from the region of gravity and put it somewhere else. People have raised questions about whether this is really what's happening. Suppose you were just standing outside the black hole collecting the radiation, you are still feeling some effects of gravity. And so is this page curve really accurate for that? And so I think we still need to understand what happens in the presence of gravity, and can we make sense of these ideas in the presence of gravity. There's been some recent work by Busso and Pennington which is going in this direction, and that's sort of what I'd like to pursue. Okay, sorry about that. Thanks a lot.
Oh, yes. So questions from the audience, especially from a certain member of the audience.
Sorry, could I ask a question?
Yeah, we're waiting for you to ask.
Oh, okay. So I was wondering whether, in gravity, space-times come with a Lorentzian structure.
Yes.
There's causality, all of the Lorentzian structure that comes with Lorentzian space-times. How much of that has been reproduced by tensor networks? I mean, the reason I ask is because tensor networks look like they're space rather than space-time.
Exactly. So this is close to this comment that I had before, which was that these tensor networks are sort of working like position eigenstates. And so it's sort of natural to expect that they don't have a good Lorentzian interpretation. Because the wave function spreads out pretty fast, and so it's non-semi-classical. You could consider taking a superposition. So there's in some sense, like when we write the general semi-classical coherent state as a superposition over fixed area states, that's just an identity. But then because you're writing it as a superposition, that's too general. Like the tensor network gives you some basis, but yeah, I mean, if you apply a Hamiltonian evolution to that, you'll get some other crazy superposition. But I don't think it doesn't give you much leverage. It can still capture geometry, I guess, but it's not been worked out in a lot of detail in general time-dependent situations. But the whole power of this comes when you have a single tensor network, which describes a spatial geometry, but then it doesn't necessarily have a good semi-classical description in Lorentzian spacetime.
Okay, I see. Thank you. And just one more question. So the about fixed area states, is there a way to say what a fixed area state is from the CFT point of view, just without saying anything about bulk?
Good. Yeah, this is also not exactly known in detail. It's sort of an abstract quantity. Like, for example, if you have the precise quantum error correcting code that ADS-CFT is working like, so if you have the decoding unitary, then you could write the state in terms of this chi, and the chi is the area. So in principle, you could write down what the area operator is on the CFT. In practice, this is a pretty hard problem, except in very simple situations like the one I mentioned, where let's say you have a thermal ensemble, like a canonical ensemble, then the fixed area states are essentially windows of energy eigenstates. That's the only situation where it's actually. In other situations, I think it's like in principle possible, but in practice hard.
Okay. Thank you so much.
Other questions from the Zoom audience?
Can you just ask?
Yeah,
I don't know if this is what Omkar asked, sorry, or the second one, but and then answer all the Zoom audience and me privately. But what I wanted to ask you was, since you really don't care how curved the bulk is, can we just take a CFT in the boundary, okay, maybe we can even take it to have a large central charge or whatever, and construct a random tensor network which you can choose equivalent.
There are actually instances of this. There are actually instances of this. So there's this paper by Tom Hartman and Jeevan Chandra, where they actually took a 2D CFT in a certain class of states and wrote down an explicit tensor network in terms of OP coefficients and so on, like an explicit construction of this tensor network, which reproduces. Like it's exactly of this random tensor network form, and it has bond dimensions which depend on areas in the geometry, and it's exactly of this.
So the randomness there is for 3.4.
It's the OP coefficients. Heavy
sum over a class of CFTs,
and then you more or less
sort of compress it. Yeah.
Compress it. You compress that data.
Yeah, exactly. Like you have a superposition
over maybe the OPs or something.
Yeah, you have some. Yeah, exactly. You want to take that sum over OP coefficients and put it into a window of the relevant ones. So it sort of compresses the data into this fixed area structure.
I see.
It's an accurate representation of the state.
And does that allow us to understand why, if we were interested in a particular CFT, why the random average works as well? Is it that you're interested in, long distance properties and you're averaging over short?
I think so, roughly. I mean, it's the same coarse graining that you do when you do like gravity calculations, like where you don't really care about the exact OP coefficient, you're sort of just taking the average over it. And I think gravity basically reproduces averages pretty well, right? Like it has this property of reproducing coarse grained objects pretty well. So it's just doing that.
Yeah, but I mean, usually when, in what I've seen about these networks, I've studied the happy code. The size of each tessellation is not the Planck scale. It's the ADS scale.
It's also true in
this. That can be, in the larger limit, that's gigantic, right? And is that what if you can make a distinction, is that what one learns from actual constructions of random tensor networks?
No, the actual constructions also give you, there also the horizons are separated by ADS scale roughly. So even there, the tensors are roughly ADS size. So it's not different in that sense.
It's a very coarse-grained.
There's a pretty coarse-grained description. In order to go, so roughly what people say often is that when we think about this ADS scale tensor, it's sort of capturing the n squared degrees of freedom in the matrix. let's say n equals 4 supplyingments. And so you have to learn to somehow break that into finer geometry structure, which is roughly like solving the BFSS model, I guess. Like you want some emergence of geometry just from a matrix. That's the hard problem thing. That's why we've not been able to go beyond just these radius scaling transfers. Thank you. Yeah.
So just one. So in the PSSI model, which you referred to as something that they use with random tensor. So there, the way I understand it is that they look at a particular state, which is this end of the world.
Yes.
And that is some random superposition of some states with some state. And now they want to compute entanglement entropy in that state.
Yes.
And that's what leads them to, because of that randomness
that
is in that fixed area state, leads them to all these combinatorics, which happens to be identical to the combinatorics of random tensors and JT gravity and all that, right? So in that sense, I think of it as a mathematical similarity.
It is a mathematical similarity. I think what I was saying was like, with this, where this magic lies was, it's a mathematical similarity for a good reason. I guess like we have a principled way of understanding that there's this match. Once you have this match, then of course it has to work out because there's this mathematical match. So I'm just saying this is like a tool for us to use in the sense that we can do simple calculations with the tensor network, get some inspiration from it, apply it to gravity, and because of this connection, it works similarly. That's sort of the philosophy.
Okay, other questions either from Zoom or physical? Committee, anyone?
I want to ask a very stupid question. It's a real application. You were talking about holography and all. Which is talk about the space time is 3 and it's 2 and all that. This has been pointed out to create kind of a quantum indeterminacy in the space-time geometry, which we can actually see as a noise in, for example, laser interferometry.
Sorry, I missed the. Sorry, can you say that again?
Okay, so all this is holographic principle was sort of tied to what they call as quantum. If you want to define that for me, quantum indeterminacy of the space-time geometry.
Okay.
Which end up, I've seen these papers, which will give space-time fluctuation. It's a noise. That we can probe using laser interferometers. That's what we do anyway.
Oh, I see. Yeah.
These calculations are not being done.
Right.
This kind of network calculation, can it be adapted? Because that can be actually, in a very, so that can be used for, I don't know how long it will take, 100 years or whatever, but can it be adapted to other than, black hole entropy and all that calculation?
These effects that you're talking about, if I understand correctly, are the area fluctuations, right? Exactly. This is the fluctuation. The thing is,
they don't need a horizon, it's actually in the log.
In just the geometry, right. So those fluctuations in the fixed area state are suppressed. As we were saying, like they're more like eigenstates, and so they don't have the spread in the wave function, which causes this indeterminacy. So really what you'd have to then do is take a superposition as we were doing for the other calculations, and the superposition over tensor networks would reproduce these fluctuations. But I'm not sure it's good because like superpositions are not necessarily, like you lose some of the leverage of tensor networks when you have superpositions because it's a pretty general calculation often. You can use it to your advantage, like there are clearly many examples that I showed you where you can use it to your advantage, but it's not obvious to me that it will necessarily be the way to solve this problem. That's just the gap I'm just talking about.
I think in fairness, it is very nice, but it's very crude approximation.
It is, yes.
You have no gravitons. You have no propagating degrees of freedom. So, computing a order G Newton fluctuation,
I agree.
But you was talking about corrections to G Newton from the page curves. I was kind of wondering something similar.
I think if you like have specifics, like for example, if you had a black hole horizon and you wanted to, this is a crude approximation, but it's still capturing fluctuations of the horizon area.
Oh, but that's really saying too much. Show me a graviton first.
No, but
anything like ADS space, forget a black hole, right?
No, but I don't think you need gravitons for
this. Calculations and corrections. Right?
It's one thing to say I have 2 saddle points in this. Don't get me wrong. Okay, in this very gross discretization where you've taken radius sized chunks of the space-time and put them on a lattice.
Yeah.
Is one thing to say that and the saddle point map. Another thing to say that order h bar fluctuations in gravity, the Planck fuzz is what you're going to be able to capture.
No, but
It's an altogether different level of sophistication that you would require. Then you would, at the very least, have to have a way of discretizing gravity. Okay. And it's been tried for years, right? Starting from Regin, there isn't a very good way.
Right.
Because then you'll be able to cure the UV problems of gravity.
I don't think they're doing that.
Calculus, that's triangulation. It's not talking about.
Okay,
but I think it's not discretization of space-time in that sense.
But
I think in that case, it's like you really want to discretize at the Planck scale, and here, this is a much more coarse-grained thing.
So I agree. It's very nice, but I'm just saying it's a very long ways.
I agree. I mean, I think roughly the fluctuations here. So in the situation that we had, the fluctuations came from taking the superposition over many tensor networks, right? That was sort of put in by hand. So the value of the fluctuations or whatever is put in by the weights by which you're weighing these different tensor networks. You need some independent calculation to tell you what those weights are, which is the gravity calculation. So in that sense, you need the gravitational description still as an input for this. So I'm not sure if it helps.
Once you just do one loops and classical value, right?
Yeah.
In the real world.
Yeah.
I think that's what you do, right?
Yeah. I don't think you need this as I don't know if this buys you anything in that case.
Yeah.
I think there you can just do GR plus QFT.
Okay. Great. Let's thank the speaker.